Okay, using a wire as an example, we define the current as the motion of charge through that wire. So the current I is equal to the rate of change of charge over time, which depends on the conductivity of the material times the cross-sectional area of the material times the electric field established in that wire. Now, the two things that I want to note are, first off, that happy day, we have another conservation law. Conservation laws are absolutely central to physics. In fact, for both semesters, the goal is to move, especially in the first semester, we start with the assumed conservation of mass. Mass is not going to magically appear or disappear. And we move toward places where we can work with the conservation of energy and the conservation of momentum. Well, here, we have the conservation of current. If I've got a junction, and current may well be flowing through that, and I happen to define, current in this case, well basically, the conservation of current dictates that the current in has to be equal to the current out. So, in this case, I1 must be equal to I2 plus I3. That seems very straightforward, but we're going to find that it's exceptionally powerful when analyzing the general flow of current through circuits. Also, if I've got some material, okay, I've got the motion of the current, the current through that material depends upon the conductivity of that material. But let me look at something. Now I've got conservation of current, important thing on its own. Let me look at this. Okay, the electric field in this region is equal to, if the electric field is constant, the change in the electric potential over the path, and let's call it the change in the electric potential over some length L. Ed. Now, I can then say that the current is equal to the current density times the cross-sectional area, or as I have it right here, the conductivity times the cross-sectional area times the electric field. Now, if I look at these two things, let me take this and put this in for the electric field so that I've got the current is equal to the conductivity times the cross-sectional area times the change in electric potential over the length L, or the current is equal to the conductivity times the cross-sectional area divided by the length of the thing that I'm looking at. So this is all material and geometry, stuff we know from the outside, stuff I can stamp on this at the factory. All of these three things, I can just write it on the wire as the wire is made, times the change in potential over the wire. Now, this defines how easily a given change in potential, or what current results in a given change in potential. I'm going to write this slightly differently because the larger this number is, then the less the current is for a given change in potential. So I'm going to define this as the resistance, and I'm going to say, okay, that current is equal to, actually, I'm going to define that, as 1 over the resistance, so that I can say that if I establish a change in potential over a length of wire, a circuit element, whatever the heck it is that I'm looking at, that's equal to the current passing through that element times the resistance, where the resistance is equal to the length divided by the conductivity times the cross-sectional area, or I'm going to come up with another term called rho, not P, but rho, the resistivity. Why? Why have two things? The reason why we have two things right here is because, if I speak of it in terms of the resistivity, then the larger the resistivity, the larger the resistance. And the units for resistance will be the ohm, which uses a capital omega, and the ohm is defined as volts per amp. Let's see if there's Yep, that is the way that they break it down. It's the simplest way to define it. Of course, I can break down amps into coulombs per second and other stuff, but this is a very useful way of dealing with that. And so that depends upon, then, again, this resistance depends upon something that we know at the beginning. That doesn't change with delta V, doesn't change with R. And this is referred to as Ohm's law. This does not work all the time. This is not a universal truth. A material for which Ohm's law works is called an ohmic material. We'll be dealing with ohmic materials, but don't think that that's all of what nature is. We have to carefully choose to end up with materials to make sure that they follow this law.